Okay, so as we mentioned last time, now we're going to talk about a special case of a path, which is a loop. So this was the picture, the last picture I showed last time. So the loop is just a path so that the initial and the final point coincide. So here is your topological space X, and there's some base point x0, and this is a loop based at x0. Now let's consider the following set. So let's say pi 1 of x, x0, this seemingly weird notation. This is the set of path homotopy classes, path homotopy classes loops in X based at x0. Now it just so this is first of all, this is a set together with the star operation we defined. So this is the operation we defined on the set of path homotopy classes of path whose initial and the final point coincide, right? So since we're talking about the loops based at the same point, we can concatenate them, and this operation can be extended to their path homotopy classes as before. So we consider the set of path homotopy classes of all loops here, all loops based at x0. So here, this is the notation for the base point. And once we have a base point, and we can have this binary operation we defined for the path homotopy classes. So here is an easy exercise. Exercise to show this is a group. So if you think about this, we already showed that this operation is associative. There's a left and right identity, and there's inverse. So just because now we have a loop, so that the initial and the final point are the same, so the left identity and the right identity coincide. So there is actually an identity, and the operation is associative, and there is an inverse. So, well, it's not really just an exercise, it's really an observation from what we have already proven. Okay, so of course, whenever you see this type of definition first, the first natural question is the choice of the base point essential? Does it really matter which base point we choose, right? So here is how we should think about this question. So let's say I have a topological space X, whatever the shape it is. So now we have one point x0 and say another point x1. So we've been talking about a path, I mean the loop, based on x0. So this is one kind of such a loop. And now we consider a path, let's say alpha, from x0 to x1. So we have arbitrarily just 2 points, and say there is a path between those 2 points, and call it alpha. And using alpha, we can turn this loop f into a loop based at x1 instead of x0. But how do we do that? So here is the observation. If you think about the alpha bar star f star alpha, this is actually a loop based at x1. So what does it mean? So here, maybe I should do this. So here we're doing alpha bar, meaning following alpha, but in the reversed orientation, and then follow f, and then follow alpha. So this actually starts at x1 here, and we have to go along alpha in the reverse direction. That's alpha bar, and we do f, and then we do alpha. So we travel along all these things. So since they can concatenate it, this is a single path starting and ending at x1. So this is indeed a loop based at x1. Okay, so that one can easily check. So what does this mean? Does alpha induces the following map. So going from, say, well, let's call this induced map alpha hat. This is a map defined from the path homotopy classes of loop space at x0 to the path homotopy classes of the loop space at x1. And whenever we have path homotopy class of a loop f based at x0, this is get mapped to alpha bar star f star alpha. Well, we can just write it as alpha bar star f alpha bracket. It's the same thing as remarked before. So anyhow, so because this is now a loop based at x1, we can think about this, right? So let's see. First, I think we can easily observe is that this is a well-defined map. So if you change the path homotopy within the path homotopy class of f, so if we choose a different representative, of course, let's say f and g are both path loops based at x0 and which are path homotopy to each other, then of course this implies that alpha bar alpha is path homotopy to alpha bar g alpha. So this implication is really the implication how we see this kind of equality between the path homotopy classes. So now we can easily see this. So, alpha hat is well defined. First non-trivial thing to prove is that alpha hat is a group homomorphism. So these are not just a set, but we observed that with respect to our operation star, it's actually a group. So what we can what we have to show is that it's actually a group homomorphism. So first thing, the homomorphism property. So how do we see that? So if I feed f star g into alpha hat, well, by definition, this is same as alpha bar star f star g star alpha. So here is something you can check. This is same as alpha bar star f and doing alpha and alpha bar and g and alpha. So I'm not putting any parentheses or anything because the it's all the same thing in the viewpoint of the path homotopy class. As a path, maybe they are different, but in terms of path homotopy class, it's nothing to worry about. Here I inserted this, well, because the going along alpha and then going back to alpha bar, this is loop based at x0, which is path homotopic to the constant path at x0, right? So this is actually really the same thing as ex0. And of course, the putting this in the middle of this thing is just the same, right? In terms of path homotopy classes. So exactly, we can see this equality. So if you group them together in this way, like this, so this is the same thing as alpha hat of the image of the path homotopy class of f under alpha hat and star with the image of the path homotopy class of g under alpha hat. So this shows that alpha hat is a group homomorphism. So details can be checked, but really just this, putting an identity in between the group element, it doesn't change anything. So that's the whole point. So we're using the fact that ex0 is actually the identity in the pi1 of xx0. So when you consider the if you recall what we have had to do to show the existence of the right identity and for the path homotopy classes with the star operation, so here the ex0, the constant path at x0 is the identity element in the pi1 of xx0. So when we talk about the loop space at x0, then that the constant path at the base point is the identity. I mean, the path homotopy class of it is the identity of this set, group. Okay, so that shows that alpha hat is group homomorphism, and actually we can indeed show this is an isomorphism, group isomorphism. The one way to see this is actually we can easily come up with an inverse of this homomorphism. What is that? Well, so the alpha hat inverse is actually the same thing as the alpha bar hat. So the inverse path to alpha bar is the same path. I mean, in terms of media, it's the same path, but you are going in the reverse opposite direction. So the alpha hat, alpha bar is an inverse path, induces a map which is an inverse to the map induced by the original path. So this is really an observation. You can totally check by yourself in a second. So this shows that the induced map alpha hat is actually a group isomorphism. So what does it imply? We were asking how essential is the choice at the base point x0. And what we have done is that if we choose different base point x1, and we can compare the pi1 of x0 and pi1 of x1, so the set of loops in X, set of past homotopic classes of loops based at two different points in your topological space, we're comparing them, and as long as we can find a path from x0 to x1, the two base point, then there's nothing to worry about in the up to group isomorphism, because they are group isomorphic, and the isomorphism can be easily found, concretely found, using the path homotopic class of this path, alpha. So if you think about this, here is the summary. I'll write it as a corollary of our discussion. This is the summary of what we have shown. So if X is path connected, meaning any 2 points can be joined by a path, then pi1 of x0 is isomorphic to pi1 of x1 for any choice of x0 and x1. So really, up to group isomorphism, the base point doesn't matter. The base point is actually important because when you change the base point, it's the isomorphism is not the identity map. On the other hand, you should not worry about the isomorphism type of this group if you're dealing with a path connected space. And if you have a space which is not path connected, then you have a several path component, and then which path component has base point will change it the group. So actually, each path component will have a well-defined optimorphism group associated with it. So it's really natural and reasonable to assume your space is path connected and then study about this group. So finally, I'll say what the name of this group is. Well, this is the fundamental group. So the pi1 of x0, this guy is the fundamental group of X with respect to the base point x0. And the isomorphism type of the fundamental group, again, doesn't depend on the choice of the base point as long as X is path connected. Okay. So this is this is the definition of the fundamental group. But on the other hand, you see this notation pi1. So actually, why there's one here? Well, there is actually a family of groups defined in a well, I mean, to some extent, in somewhat analogous way. So it's called the pi-n. So this is the first group in this family, and this whole family is called the homotopy groups. Homotopy groups. So the pi1 is really the first homotopy group of the topological space you're talking about. We're not going to define homotopy groups in general until the algebraic topology 2 for a graduate student. So it's really not going to be the topic you have to worry about. But just I'm just mentioning this fact because it's such a weird notation, pi1, even though we're not going to talk about pi2, pi3, pi4, etc. But this is really a first element in the important family of groups which are topological invariant of the topological spaces. So anyway, so that is the definition of the fundamental group.